welcome back to Mr. Mick's Classroom. In this episode, I'm going to teach you how to convert decimal numbers back to binary numbers. So last episode we learned, hey, what was binary number? It's our strings of ones and zeros we use to send data over the internet or to store data on computers. In this episode we're going to say, instead of converting binary numbers to regular numbers, that's what decimal means, how do we take our regular numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and convert those back to binary numbers. Right? So let's just take an example here. We'll take the number 14. Right? So I'm going to take the number 14, and now I want to convert that over to a binary number. So first what I want to do is I like to put my little dashes in here, kind of figuring out how many bits I'll need. Now I know the highest 4-bit number is 15, so I know that it's got to be at least 4, but if you create more than 4 bits, that's fine. It just ends up with zeros on the left side, and you can erase them later. So what I'll do here is now I'm going to put my, my 2's beneath it, so my powers of 2. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. I always like to show what these equal. So as we talked about in the last video, any number to the power of 0 is always 1. So 2 to the power of 0 is 1, and then 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. All right. So what I have to do here is I'm trying to get 14. So my goal is I got to start from left going to right, and any number I can use that will help me add to 14, I have to use that number. So 8 is less than 14. I could use that to help myself add to 14. Therefore, I have to. If I'm using that number, then I'm going to put a 1 above it. All right? Now we go to 4. 4 plus 8 equals 12. That helps us get to 14. Therefore, I have to use it. Right? Since I can use it, I have to use it. So that's 1, 1. Then 2 plus 12, so 8 plus 4 is 12, plus 2 is 14. Again, I can use it, so I have to use it. That equals 14. That means we're not using the 1 over here. Since we're not using this 1 over here, that makes it a 0. So the binary equivalent to 14 is 1110. Again, that's not 111. That's not 1110. This is binary number of 1110, which is equivalent to the regular number or decimal number of 14. Let's do another one so we can see that together. Let's do the number, I'll pick a kind of easy one. Let's pick an easy one, 64. Looks harder because it's bigger, but it's actually easier. Right? So I'm going to set it up just like I did before. I'm going to use my dashes, and let's say I don't know how many I need. I don't know how many I need. Oh, let's put you back up here. I don't know how many I need. We'll put 64 up here. So I know I want to get to 64, so I can remember that. It's not a very good 4. There, that's better 4. All right, so I'm trying to get to 64. Let's see. And let's say I don't know how many bits I need. So we'll say 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5. All right, let's see if that's enough. So we know that this is always going to be 1. 2 to the power of 0 is always 1. 2 to the power of 2. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. Then 16. Now we're just doubling, right? Then, well, we've been doubling, but then 32. By the way, what do these numbers look like? 16, 32, 64, 128, right? These are similar to our hard drive sizes, right? 256, 512. Okay, so I don't have enough numbers, right? I don't have enough numbers, so I got to add one more. I know I don't have enough numbers because my highest one here is 32. If I add all these together, I'm going to get 63. And I'll show you how I know that a little later, but you can do the math if you want to yourself. But anyway, so I want to add one more bit. Alright, so that's 64. Alright, let's keep it consistent with the colors. Don't want to throw anybody off here. Alright, Oh, that's 64. That means this makes it real easy, right? So if that last number is 64, then I know all these numbers leading up to it are going to be 0. And so therefore, the binary equivalent to 64 is 1, 0, 0, 0, 0, 0, 0. That easy. All right. So earlier, I had said, hey, I know that this is going, this right here is going to equal 63. Let's see how I knew that. Right? So kind of going to a different thing now. Just kind of, this is like a how to manipulate numbers or understand numbers. Right? So the next number over is going to equal to one less than all of the, or one more, sorry, the next number over, right, 2 to the power of 7, is going to be equal to all the rest of these numbers here combined plus 1. All right, so let's look at that to understand that for a second. All right, so let me use a different color. So let's say, for example, 1 plus 2, that equals 3, right? 1 plus 2 is 3. That's 1 less than 4. 4 plus 1 plus 2, that's equal to 7, right? So these 4, wow, I'm really bad at that. These 4 equal to 7. That's 1 less than 8. Right? 4 plus 2 plus 1 is 7. That's 1 less than 8. So 8 plus 7 is 15, right? So these numbers all together are equal to 15. That's 1 less than 16. You'll see this keeps going. 15 plus 16 is 31. That's 1 less than 32. Right? 31 plus 32 is 63. 1 less than 64. So I know, and it's easier to double numbers, but that helps you know what all these numbers are equal to as well. Because I know 2 to the power of 7 is going to be 128. Because 64 plus 64 is 128. Right? So I know that. That's really easy. But then that helps me understand what if these were all 1s, for example. So let's change this. We're done with that now. So let's say these are all 1s right here. I'd like things to be consistent. 1 second here. Huh? Right? So I know that saying this is going to be a 0 here. These are all going to be equal to 127. I know that because it's going to have to be 1 less than 128. Right? So that was one little principle to understand with the numbers. Hey, thank you for watching Mr. Mig's Classroom. Remember to like, subscribe, and share my videos.